All right, so I start. So first of all, why do we study granular suspensions? Well, first of all, they're present in nature. So this is, for instance, a picture of the Gulf of Finland, where you see swirls of phytoplankton. So these particles are not only pretty, and they're also important because they store some of the CO2 we produce. So it's very important to understand how they are transported in the ocean. There are examples here in geophysics. So this is an explosive eruption of ashes somewhere in Indonesia. I found this interesting video, if it works, yeah. So it's a river in New Zealand, and it's quite intriguing because you see the density of rocks is extremely large, although the river can flow extremely fast. So it's a pretty puzzling behavior we see. So there are suspensions also in biology. So there is blood, of course. You know, what you might not know is that there are also suspensions in some plants. Some plants have grown very big cells. This is like 1 millimeter. And the dynamics of the suspension here could be important to understand the transport of nutrients on this large length scale, and so understand the metabolism of these plants. All right, so many examples in nature, many examples also in the industry. So one first think of concrete, of course, the most widely used material. So concrete needs to be hard to make beautiful structures like this. So it's a picture of the museum. It's a new museum in Marseille. So maybe you can visit during your stay. Actually, it's better for the view from the rooftop and the restaurant than the exhibitions, but it's worth going. So concrete needs to be hard like this to make these structures, but it also needs to have very good flowing properties and to mold it. And so we'll come back to this later on in the talk. So many examples: paints, food industry, and so on. All right. So also maybe there is a scientific interest of studying granular suspension because it's a quite new domain at the crossroad between fluid and solid mechanics. It calls for concept of soil mechanics sometimes and statistical physics. And as we will see, it's still not very well described, and often we use phenomenological laws. So there is still need for theoretical developments. And so here is a very short list of maybe the main difficulties. Of course, there is a very large number of particles, and we don't want to describe all of them. And on top of that, most of the time, thermal fluctuations are absent. So we cannot use the tools of classical thermodynamics or statistical. And we'll see also that the interactions between the grains can be complex, either through hydrodynamic interaction or through contact, and that can be difficult to describe. All right, so first I plot here the particle size range, which covers a big spectrum, and so I can define here more precisely what I call granular suspension. So it will be the simplest case of large grains, typically larger than 100 microns, so that these grains only interact through the fluid, through hydrodynamics interactions and contact. If you go this way, things get a bit more dirty because you enter the world of colloidal suspensions, where you have thermal agitation, repulsive force, adhesion force. So I will not talk about this, but I will come back to this intermediate range here, which is interesting, between 1 and 50 microns, because the grains can be non-Brownian, but they can still interact through a repulsive force. And we'll see that that gives interesting properties to the suspension. All right, so this is for the particle size. Particle density, of course, distinguishes two domains. So sedimentation, the particles are heavier than the fluid, and rheology, or neutrally buoyant particles. Okay. And so what I will try to show in this introduction is that although these two systems historically they have been described with the same kind of approach and tools, we now better understand that the physics, the underlying physics of these two systems is quite different. we'll see that sedimentation is mostly governed by long-range hydrodynamics, and whereas rheology is mostly dominated by geometric aspects related to the fact that particles cannot interpenetrate. So I'll try to show this. So I mainly talk about rheology, but I'll do a short turnaround to discuss sedimentation. So I recall the sedimentation of one grain in a viscous fluid. So this was solved by Stokes, 1851, in the limit of low Reynolds number. So there will be no inertia here, no turbulent flows. So the grain is driven by gravity, and this force is balanced by the drag of the fluid in the opposite direction. And so this sets the famous Stokes velocity of one grain. But the point I want to make here is that when the grain falls, it generates a fluid disturbance in the flow. It's like the blue arrows here, which at first order is given by the Stokeslet, like if the particle was a point force. Okay? And the main feature of this Stokeslet, you see that the fluid disturbance decays very slowly, like 1 over the distance to the particle. And this means that if you have a collection of particles, each particle will interact with the other grains, even if they are far apart. And so sedimentation, here we see it falls in the case of an n-body problem, which interact through long-range interactions, and the interactions are mediated by the fluid. Okay.
How long does polarization remain?
Here, everything, it's low Reynolds number, so everything is instantaneous. So it's in the limit of low Reynolds number. So the fluid disturbance is instantaneously created. Okay. So maybe some connections with your electrons. Okay. So let's see what these long-range hydrodynamic interactions do. We can look at the evolution, the sedimentation of a cloud of n particles. So initially, I distribute n particles in a spherical volume like this, and this was actually the last problem that Bachelor studied before he died. And the question he was asking is, how long does the blob remains like a cohesive entity as it sediments? So how long does it take for the particles to disperse in the surrounding? And so you can write for the fluid motion, you can use the Stokes equations, because here again we are limit of no inertia, no Reynolds number. And here you write the force field in the fluid, which is 0 everywhere except at the center location of each particle, using this delta Dirac function, assuming that each particle is like a point force pushing the fluid downward. Okay. And if you do that, it's easy to get the velocity of each particle in the cloud, because it's simply the Stokes velocity, as if the particle was alone, isolated, plus the sum of the disturbances generated by the other particles. So the sum of the Stokeslets, which are also the green function of the Stokes equation. All right, and you can sum because of the linearity of the equation. So when the number of particles gets large, this term is negligible. And so you can normalize these equations, and you end up with a set of equations for the particle velocity. It's a very simple problem because there is only one parameter. It's the number of point particles, and you put in your cloud. Okay. And this is a normalized Stokelet, which is a scaled invariant function, so it's nothing complex. So from this, you can choose the initial configuration of the particles, and then integrate the motion of each particle in the cloud. Okay. So this is the side view here, and this is the bottom view here. Yeah. Yeah, exactly. So the Stokelet is the first order flow disturbance generated by a particle. So it's the disturbance generated by a point force. So it's like a green function of the Stokes equation. Yeah. There is no potential here. It's just a free disturbance. It's a velocity field. It's the free disturbance. Well, if you are here, it would be repulsive because it's pushing the fluid like this. But if you are here, it would be attractive. And this answers you. All right. So you're ready to see this? So I start the simulation. Okay. So what we see is that as a result of these hydrodynamic interactions, long range, there is this very strong collective motion that spontaneously emerges. Okay. The particles recirculate like this in a toroidal motion. Some grains are left behind, and it makes a torus which grows. And if you wait a little bit, you see this. So you see the cloud of particles destabilizes into two droplets like this, and each droplet will follow a similar evolution, making a torus and breaking up again. Okay. So this is the result for the simulation, assuming each particle is like a point force generating a long-range disturbance. So we can see if this captures the reality. So we can do the experiment, inject a cloud of particles here, let it sediment in a big tank filled with viscous liquid, and we just track the evolution with a camera. And what we find actually that there is a very good match between the experiments and the simulation. So we have the initial spherical cloud that goes into torus, destabilized into droplets, and so on. All right. Yeah, you see that because this is like a collective motion, so you need a minimum. The less particles you have, the more fluctuations you have, and so then there is not enough particles. You don't see this beautiful toroidal motion. So there will be. We have seen 1, 2, maybe 3 destabilizations, but then there are not enough particles. Yeah, good question. Okay. All right. So this short first part on sedimentation was just to show you how, at low Reynolds number, sedimentation of grains in a fluid are dominated by this long-range hydrodynamic interaction, and how a first-order description of the fluid disturbance generated by the grain capture well the dynamics. And in sedimentation here, what's interesting is that there is a permanent coupling between the microstructure, the position of the particle, and the flow, which, although all the equations are linear, it leads to complex behaviors. So you can produce instabilities and complex patterns like this in the system, right? So I can now move to rheology. So now we have naturally buoyant particles. And so when we do rheology of a suspension, the basic question we ask, usually we put a suspension like this between two plates. We fix the particle volume fraction phi, right? And the question is how fast, what is the shear rate if I apply a given shear stress? And so this resumes to defining the constitutive laws of suspension, which relate the shear stress and the particle pressure to the shear rate through what we call the suspension viscosity, okay? Which is the fluid viscosity times a dimensionless function of the volume fraction of particles, which is the sole dimensionless parameter here, right? So it's eta S of phi for the shear viscosity and eta N of phi for the normal viscosity, because you also have particle stress that develops, okay? So what is the evolution of this dimensionless viscosity? Well, first, I show you the historical hydrodynamic approach, like close to the one used for sedimentation. So now we have one particle here in the shear flow, and it's naturally buoyant. So there is no external force. There is no gravity acting on the particle. Yet the particle is rigid, cannot deform, so it generates a flow disturbance also. But this flow disturbance now is called the stresslet, which decays like 1 over r squared. And so Einstein was the first one to propose the first order correction in phi, predict the suspension viscosity, precisely taking into account the additional dissipation in the fluid due to this stressless disturbance. Okay, so this was in 1906, and then it took about 70 years for Bachelor to predict the second order term, which calculation which is more complex because you have to describe the pair interactions. And then if you want to go further, you need to account for the multi-body interaction because it's a long-range problem. And today there is no exact solution. So in the meantime, the experimentalists they've done something. So you determine the empirical laws for suspension. So you place the suspension in a rheometer, and you can measure directly the viscosity of the suspension. Okay. And so this is the viscosity of the suspension as a function of the particle volume fraction. And it's interesting to see this is an Einstein prediction. This is a Bachelor. And you see that this hydrodynamic approach is not able to capture the main feature of the viscosity. And the main feature of the viscosity is that it diverges here at a critical packing fraction. And it's also the jamming volume fraction. Beyond that, the suspension no longer floats. Okay. So there was many empirical laws proposed, but you can write that the suspension viscosity goes like phi c, the jamming volume fraction, minus phi to the power of minus 2. And this tells you, in fact, that the viscosity, in a sense, is set by the distance phi c minus phi. So how far you are from the jamming limit. Okay. And so this brings me to a more recent approach to describe suspension. It's a granular approach because it's inspired from the dry granular community. So standing from the other limit, in a sense, from the jamming limit. And in this community, they simply consider that in most flow in nature, it's not the volume fraction phi that is imposed, but it's the particle pressure. So if you take a pile of grain, the particle pressure is fixed by the gravity, by the weight of the grains, but the volume fraction is free to adapt depending on how fast the flow goes. Okay. And so what would be a particle pressure imposed rheological configuration in the lab? It's the same as before, except now the top plate here, it's a grid, it's not a plate. And this grid is impermeable to the grain, but it's permeable to the fluid. Okay. And so the grid is free to move like this to shear the system, but it's also free to move vertically to allow the volume fraction to adapt. And so we can use the grid to impose the particle pressure. Okay. So in this system, the volume fraction is not fixed. So the control parameter is the viscous number, J, which is eta F gamma dot divided by the particle pressure. You can see it as a rescaled shear rate. And there is another point that is interesting in this pressure imposed configuration is that now the constitutive law that characterizes the suspension is a friction law, because you see, you want to relate the shear stress to the particle pressure. So just like in Coulomb law for friction, this defines not the viscosity, but the friction coefficient of the suspension. So mu of J is really the friction coefficient of the suspension. And you need a second law to tell you how the volume fraction changes when you change the shear rate, for instance. Can you see? Okay.
The figure before that you described of the suspension approach.
Yeah.
Is it the lack of ineffective mass? But it's not taken into account correctly?
No. We'll see. We'll see. We'll see where it comes from afterwards. Yeah. Hope I can show you. Okay, so like this, we have frictional rheology, and we characterize the suspension friction coefficient. Okay. So these measurements, pressure imposed measurements, they have been done so recently by Boyer, Guazzelli, and Pouliken in 2011. This is a pressure imposed rheometer where you press the grains with a grid and you rotate, and so you access the suspension friction coefficient mu and the volume fraction as a function of G. Okay, you see that they follow simple power laws of the viscous number. So there would be many things to describe here, but maybe the main point is that with this pressure imposed configuration, the very important point is that there is no divergence here close to jamming. Jamming is when J goes to 0. And this is because mu, by definition, is the ratio of tau over pp, okay? Two quantities that diverge when you do volume imposed configuration. But here, the divergence cancels out. And so you see that the friction coefficient of the suspension remains finite, even at the jamming point, okay? And so this allowed to make a lot of progress in understanding the rheology of suspensions, because we were able to make measurements very close to the jamming point, and so we could access the critical exponents that characterize this divergence. Okay. So I told you there are imposed volume measurements where you characterize the viscosity. Pressure imposed, now you press the grains and you characterize the friction of the suspension. And actually, these two approaches are completely equivalent. You can go from one framework to the other in both ways. Just giving an example. So from pressure imposed measurements here, you can access the suspension viscosity simply by taking the ratio mu over J. You see, mu over J is tau over gamma dot, and tau over gamma dot is the suspension viscosity. Okay. And you recover with the same data, you recover the divergence at the maximum packing fraction with the exponent -2. Okay. So maybe one last word to tell you a bit more about what's the origin of this divergence of the viscosity. And so to illustrate this, I show you this movie of granular suspension that is shear. And the nice thing that we can see the flow of the interstitial fluid. And you see that although it's low Reynolds number flow, zero Reynolds number flow, there is lots of fluctuations in the fluid phase. And so what's interesting here is that you can plot the distribution of local shear rates that you measure in the fluid, normalized by the macroscopic shear I imposed. And when you plot this distribution here as a function of the volume fraction, you see two things. You see that the local shear rates in the fluid, they are on average, they are larger than the macroscopic shear I impose. And the local shear rates, they get larger and larger as I increase the volume fraction. So the more I put grains in the system, the stronger the fluctuations in the fluid phase, okay? And so there was this nice idea put forth by De Giuli, Werner, and Viart in 2015, where they said, where we can compute the power dissipated by the system. And you can compute it in two ways. Either you consider the suspension as a whole, right? And so the power is the suspension viscosity, eta F, eta S of phi, times the macroscopic shear square. Okay? But you can also say that in fine, the dissipation occurs in the fluid phase, right? And so the dissipation due to the fluid phase is the volume of the fluid, 1 minus phi, times the fluid viscosity, alone this time, times the local shear rates, okay? And so like this, you can extract that the suspension viscosity actually goes at the local shear rate square divided by the macroscopic shear I impose, which are amplified. And so this defines what they call the lever function, because now to understand the suspension viscosity, all the question resumes to understand how the velocity fluctuations in the fluid are amplified when you put more grains in the system, and as the volume fraction goes to jamming. Okay. And so they did that, proposing floppy mode theory that comes from amorphous solid. It's also called soft mode theory. So I will not detail here, but I just give the idea. So, so floppy modes, they are all the geometrical modes of displacement of the grain, which ensure that grains do not interpenetrate and overlap. Okay. So if you are in a dilute system like here, if you have a particle that needs to go from A to B, well, there are many potential modes the particle can take, and you see that the non-affine displacement, so the excursions away from the mean streamline, they are kind of weak because the system has lots of room to accommodate. Now, if you are packed, you see that there is a lot of geometrical frustration due to the fact that grains cannot overlap. And so now to go from A to B, there are only a few potential paths you can take. And this path will have very strong excursions because particles must avoid each other. And so just based on this idea that particles cannot overlap, they manage, this is what I do not detail, they manage to evaluate the scaling for the lever function. So how velocity fluctuations are amplified as you increase the volume fraction. But once you have that, they find that the suspension viscosity diverges like phi c minus phi to the power of minus 1. So this is the origin of the divergence here. Seems to be more into geometrical aspect of the problem, and the long-range hydrodynamic interactions do not play any role.
Okay. So in the slide before, we have a grade like gold, like two gold that can never overlap. We have
oh yeah. In the movie, in this movie, these movies. So the grains are the black stuff. Yeah, you're right, and they are hard grains. They are hard PMMA grains, and they cannot overlap. Maybe you have the impression that it overlaps because it's just a slice, 2D slice in a 3D suspension. So some grains change. Yeah, okay, but everything is rigid here. Okay, good points. All right, so maybe this brings me to the end of this short introduction for the basics concepts. So sedimentation is governed mostly by long-range hydrodynamics. And here it seems that it's more the fact that particles make solid contact and the geometrical aspects that dominate the system. All right, maybe there are other questions, or I can move on.
So you were just discussing about the different trajectories function packing. Is there anything like a minimum principle for the path that is chosen?
Like what, for instance?
Well, I mean, it's something like Vermont's principle, path of median time, and the question of the path of median time and normal. Is there anything like that?
Yeah. This I don't know. I don't know exactly how they. So here they use. They really look at the distribution of floppy modes. It's quite a complex development. So there are two things. They use the distribution of floppy modes. They look how it's distributed, and they also look at the distribution of weak contacts. And so, and they, I don't know if they use a principle like this. It's a good question. I don't know. All right. So for the following, so in the few last year, there was also quite a bit of progress in understanding suspensions. And the main message maybe is people, the community has understood for rheology how particle friction is very important, and it can completely affect the macroscopic behavior of the suspension. So I'll try to show you that. I've prepared 3 examples so we can see how far we can go. So I first talk about shear thickening suspensions. You probably all know, I don't know if you know shear thickening suspension, so at least you can all make it if you have this in your kitchen. So these are cornstarch particles. They are about 15 microns in size. And if you put these particles in water, you get a suspension that has a very weird behavior. You see the viscosity is very small at low shear rate. So when you increase the shear rate, there is a critical shear rate where it becomes almost a solid. The viscosity increases, and if the volume fraction is large, it can turn into a solid. So this is very spectacular, and this has become very popular. So there are even commercials now based on this property. So show you it's a commercial for a bank. If you fill a pool with this suspension, if you run fast enough, it solidifies so you can cross the pool. And so it's pretty, and of course, like this kid, you don't want to do that. If you stop moving, the shear rate is low, the viscosity goes back to low value, and you see. Okay. So this shear thickening, so this increase of the viscosity was studied since the 30s, and it was a very big puzzle in the community for a long time. And the puzzle comes from the fact that if you consider it from the granular suspension I told you about, the viscosity is a function of the volume fraction, right? It diverges at the critical packing fraction. But if you take a given volume fraction, dimensionally, you see that the viscosity must be independent of the shear rate, because there is no other time scale other than the shear rate here in the system. So you cannot explain the increase of the viscosity with the shear rate. And so the key idea to explain shear thickening was proposed recently in 2013 by the group of Jeff Morris in New York. And the idea was to introduce a short-range repulsive force between the grains. The idea now is the grains are small enough, 15 microns, that they can interact through a short-range repulsive force. So it can either come from a coating of polymer or electrostatic charges at the surface that generates repulsive. And so now you have an additional force scale in the problem, shear thickening, because if you apply a small shear, the repulsive force just repels the grains. And so the grains can slide easily against each other as if they were frictionless. Okay. Now, if you increase the stress, you overcome the repulsive force, and the grains here will make solid frictional contact. Okay. So because there's this additional force scale, we understand now shear thickening as a frictional transition between a frictionless state of the grains at low stress, and it transits to frictional state of the grains at large stress. Okay. And so why is it so dramatic? Why does it cause such an increase of the viscosity? The point is that the jamming volume fraction depends on the friction coefficient between the particles. Okay, so before we had the suspension for granular suspension, it diverges at phi C, which is 58%. But now if the grains are frictionless, easier to pack frictionless grains. So the viscosity diverges at larger volume fraction. It's a random close packing. And so shear thickening suspension, it's interesting because it has the choice between these two branches, right? If you are at low stress, there is no friction, so the viscosity is given by the low viscosity branch. And if you increase the stress, the grains become frictional, the jamming volume fraction decreases, and so now the viscosity jumps on the upper branch, frictional branch. Okay. And so you see that you can have now you can have a rate dependence, and the jump here can be as big as you want, because here you even jump to infinity, becomes a solid. Okay. So this was put in the frictional transition model by Bjarke and Kate the year after, and it's a very simple model where they write that the jamming volume fraction phi c it's no longer constant, but here it depends on the stress you apply, and they just write sort of a mixing law that interpolates between the frictionless jamming volume fraction and the frictional jamming volume fraction, right? With an order parameter that the fraction of frictional contact. It depends on the stress. Okay. And now if you just put this jamming volume fraction that can vary into the equation for the viscosity with phi c, which can vary, you get these rheograms in red, which you see capture very well the shear thickening, the increase of the viscosity. So you have a low viscosity here, frictionless state at small shear rate. And when you increase the shear rate, you transit to a large viscosity frictional state. Yeah. So I thought about this. So the same model, here it's viscosity as function of gamma dot, but you can plot the shear stress tau as a function of gamma dot. Okay. Tau is just eta times gamma dot. So the shear stress, these are small standard rheograms. And what you see is that when the volume fraction is low, the rheology, we say it's close to Newtonian, because when you increase the stress, the speed increases linearly with the stress. Okay, so it's linear like this is a Newtonian speed. But when you increase the volume fraction, you see that there is a critical volume fraction here called the discontinuous shear thickening. So this is when there is a finite jump in viscosity, where the rheograms, they become S-shaped. And there is even a region here where the rheograms are negatively sloped. And so this is very weird fluid, because in this region, if I put the fluid between two plates, if I increase the stress, it will flow slower. Okay, so it's really not intuitive. It's because you activate all the contacts, the frictional contacts, and the suspension slows down. And so we'll come back to this later on in the. All right, so this is for the model, the theory, let's say. In the lab in Marseille, what we have tried to do is validate, try to experimentally, can we validate this theory? And so we used silica beads. It's a model shear thickening suspension. The grains are 25 microns. And silica is nice because when you put it in water, it gets charged on the surface. So you have an electrostatic double layer that generates a repulsive force between the grains. And experimentally, it's very nice because you can control the range of the repulsive force, the Debye length, simply by adding salt to the fluid. So we can tune the strength of the repulsive force. Okay. And we have also measured the roughness of the grains, which is 4 nanometers. And so to validate, it took a very long time, a few years to validate this frictional transition scenario, because you need to access friction. And usually in rheology, you access viscosity. So people are kind of stuck. And so to access friction, you do pressure imposed measurements. Okay, I've explained. But we could not use the rheometer of Boyer because the grains are very small, so it doesn't work. So we used a different pressure imposed configuration, which is simply the rotating drum. So we fill the drum with the silica particles. It's half filled. It's fully filled with water. And then we slowly rotate the drum until we make a steady avalanche, right? And in this configuration, you see that the tangent of the avalanche angle, it's a ratio of tau over p, which are just the weight, the projection of the weight of the granular layer, right? So this means that simply by measuring the angle of avalanche, you have access to the friction coefficient of the suspension, okay? And so we measure the angle and we have access to the friction, and these are the results. So this is the angle of avalanche as a function of the salt concentration. And what you see that in pure water, so when the repulsive force is the strongest, you see that you can have a steady avalanche with an angle of avalanche as small as 6 degrees. It's a very small angle to have a steady avalanche, right? And actually, 6 degrees is precisely the theoretical prediction for an angle of avalanche of an assembly of frictionless, perfectly frictionless particles. So this shows that here the repulsive force makes the grains behave as frictionless grains, okay? And then we screen the repulsive force by putting ions in the fluid, and you see that the angle of avalanche increases. And when we have completely removed the repulsive force, the angle of avalanche is 30 degrees, which is typically what you find for standard granular suspension of frictional objects. Okay. So this shows the frictional transition by changing the strength of the repulsive force. Okay, and what we find is that this transition between frictionless grains and frictional grains here, it occurs when the Debye length crosses the length scale, which is set by the particle roughness. Okay, and so it's pretty interesting to see how here very small features, but the nanoscale control the macroscopic response of the system. So here it controls the angle of avalanche, right? But it also controls the rheology, because if you take this system here where there is a repulsive force between the grains, the rheology is shear thickening, right? The viscosity increase if you shear it faster. But if you remove the repulsive force, the shear thickening disappears. So these results really make the link between the presence of the repulsive force, the fact that there can be a frictional transition, and that can induce shear thickening. All right. So this shows, I mean, beyond that, it's very interesting for the community because people have realized how much friction is important in suspensions. And this was not easy at first for everybody to realize. And this has opened many possibilities. So I give a few examples. Maybe you're interested by, I come back to the Musen. One possibility maybe now is to optimize modern concretes. So I try to explain that. If you take suspension of calcium carbonate and water, you see that it jams at a very low volume fraction. At 56%, it's already a solid. And what people do with modern concrete is that they add polymer. It's called the superplasticizer to the suspension. And what you see is that at the same volume fraction, with a tiny amount, very tiny amount of polymer, the suspension that was jammed now is completely liquid. And so the interpretation in the framework of the frictional transition model is that the system now was frictional, and by putting polymer, you generate a repulsive force. The grains become frictionless, and now the viscosity is given by the low viscosity branch, right? But now it's interesting because now that you're on the low viscosity branch, you can add more grains. You can add more particles to the system. You can increase the volume fraction up to 72%, still a liquid. Whereas at 72% without polymer, it looks really like wet sand. So it's pretty amazing. And so this polymer, this superplasticizer, there are these two gains in a sense. Not only you have a suspension that it's more liquid, so it's easier to mold, but on top of that, it's more dense. And so this means that you can make a more concrete that is more that is stronger, more robust. And so this is now how they make these buildings, which can be very thin structures that can hold very strong constraints. All right. Another possibility is now to control the flow property of the suspension by controlling the friction. So I will show you a very strange movie here. So you've seen that a shear thickening suspension is liquid at rest, right? But if I impact it, I get the frictional transition, it hardens. But here it's the opposite. So I take a spoon of shear thickening suspension. You see it's a solid in the spoon. But if I impact it with another spoon, you see it completely liquefies like this. It's quite amusing. It's completely opposite. So the way we understand this is that when it's a solid, there is a capillary interface that maintains a large level of stress in the grains. So it maintains the grain frictional, and the system can be jammed. So when I impact it, it sends acoustic vibrations in the system, which opens some of the frictional contacts. It allows the system to relax in a frictionless state, and the viscosity drops like this and becomes liquid. I have Reynolds number. I have no idea what the Reynolds number exactly, but when it flows, it's not very large. Huh? It's still a low Reynolds number limit and very viscous. I mean, the viscosity of this stuff that flows is typically 500 times the viscosity of water, so it's still pretty viscous. So this control of the rheology was done a bit more quantitatively by the group of Itai Cohen in Cornell, and where they studied how they can unjam at will the system. So they rotate a tool in a shear thickening fluid. It's completely jammed, so it doesn't rotate. And if they send acoustic vibration with a speaker, then the system can flow. And they can, like this, control the rheology with vibrations. All right. So the last point I will develop a little bit more is we try to go outside the rheometers a little bit and do a little bit of hydrodynamics. So we have done this during the postdoc of Baptiste Darbois-Texier, simply studying the flow of a shear thickening suspension down an inclined plane. Right, so I show you this movie. So you see the suspension flow slowly down the plane, and spontaneously you get emergence of waves, very regular waves, which are long wavelengths because it's about 10 centimeters, the wavelengths, and the layer is less than 1 centimeter. And so these waves, they were observed before in 2005, so before the frictional transition model, but they could not understand at all the origin of these waves because there were no flow rules to explain these waves. And so now we have Yart and Cates flow rules. So I recall they can be S-shaped, and there is a region where here the slope of the rheogram is negative. So d gamma dot upon theta is negative. And we know also from experiments that these waves can be observed at very low Reynolds number of the flow. So there is no need for inertia. And so if there is no inertia, you can write the force balance for this base state of a uniform layer, right? And here you see that the gravity that drives the flow is balanced by the basal stress. Okay, it's a depth average thin film description, classical. If you put a perturbation of the thickness, and here you have changes of the thickness, so it leads to a hydrostatic pressure gradient in the force balance. And just with that, you can propose an instability mechanism. And so it's quite easy to follow if we take it slowly. So if you look upstream of the bump, here, the thickness increases, right? So the hydrostatic pressure gradient term is positive, okay? And so this means that relative to the base state, when you put a perturbation, the basal stress, tau b, decreases, okay? Because just you have a negative sign of a positive term, it decreases tau b. So tau b decrease, but if you have a negatively sloped rheology, when you decrease tau, the suspension accelerates. It's like this. So the shear rate increase. And so you see that by putting a perturbation, I create an inward flux below the bump. And you can do the same reasoning and it creates downstream of the bump and makes the same inward flux. And so we see just by hand like this, we see that the flow is unstable if the rheology is negatively sloped. Okay. So more quantitatively, we can do the linear stability analysis, depth average, again, no inertia. And what you end up with for the equation of the layer thickness, it's interesting because it's a diffusion equation. And so moving in the reference frame of the waves. And the diffusion coefficient is A, the slope of the rheogram, divided by tangent theta. And so if you take a Newtonian fluid where when you increase the stress, the fluid flows faster, A is positive. So if you put a perturbation, the perturbation diffuses and it's stable. The flow is stable without inertia, right? But here, you have a shear thickening suspension. And if you're in the region where the rheogram are negatively sloped, you have a negative diffusion coefficient. And so the bump will anti-diffuse and be, this is how we understand how it's amplified. All right. Okay, so what do we find in the experiments? In the experiments, we measured systematically the onset Reynolds number to see the emergence of the waves as a function of the volume fraction, and we also measured the velocity, the speed of the waves. And what we find in the gray region, when the volume fraction is low and the rheology is close to Newtonian, and in this case, we also see waves, but these waves are the classical Kapitza inertial waves that emerge above the Kapitza criterion, which is a critical Reynolds number, which is the blue dashed line here. And you see it works not so bad with the data. The novelty here is above VDST, above the discontinuous shear thickening. When the rheogram becomes negatively sloped, we see the emergence here of a different branch, which is not predicted by the Kapitza instability. And the flow can be unstable at low Reynolds number. It's a different, very different instability. And actually, the stability analysis I just presented can capture, this is the red curve, can capture this branch, and also the drop of the speed of the kinematic waves. All right. So just to sum up on this, it's quite an interesting stuff because here we see that from the frictional transition, the grains interacting through the repulsive force, we can have a frictional transition which leads to S-shaped rheograms. If you couple this with the free surface deformation, then you see that you have kinematic waves that can emerge even without inertia. And usually kinematic waves, there is always inertia involved. So here it's quite and it's quite a generic mechanism. And so it will be interesting to see if we could extend that to other systems, which are velocity weakening, like some missiles or some granular media, also velocity weakening. All right. So I have maybe 5 slides on hysteresis. Maybe we can stop here and discuss, or I can talk a little bit about. This is also an interesting thing. It's yeah. I can continue. Okay. So I'll show you also some recent results we had with these same silica particles, which surprised us and sort of questioned a lot our understanding of hysteresis. So here I talk about the hysteresis of the avalanche angle. So just simply relates the fact that to initiate the flow of a granular layer, you need to incline it at an angle theta start, which is larger than the angle at which the avalanche will stop. Right? So you can all do the experiment with a box filled with sugar. You incline it, the avalanche start, and it will stop at a smaller angle. Okay. And okay, it's a very trivial observation, but it's still not very well understood in the granular community. It's a very old problem, but it's still not very well understood. It was studied a lot because it has very dramatic consequence on geophysical flows because or submarine avalanche. In a sense, the amplitude of the avalanche depends on delta theta, the difference between theta start and theta stop. And so far, most models to explain hysteresis were based on inertia, the scale of the grain. So once the avalanche is flowing and has momentum, it's more difficult to stop it, so it stops at a smaller angle. And there were this nice study by Courage-Dupont showing that the amplitude of the hysteresis, delta theta, decreases when you decrease the Stokes number, which precisely measures the inertia at the grain scale. Okay. And so all of this suggests that okay, there would be no hysteresis in overdamped system. If there is no inertia, there should be no hysteresis. And this is not what we observed with the silica particles. So I can show you, launch the two movies. So this is the frictionless grains. And so they flow with a steady avalanche angle. So here there is no hysteresis, right? But here we have the same Stokes number, which is very small, you'll see later on. But we have just turned on the friction between the grains by removing the repulsive force. And we see that there is a very large hysteresis amplitude. So you load the avalanche, there is no flow, then boom, it goes and repeats like this. And so we're quite surprised because the Stokes number we have here are very small. So this is the data of Courage-Dupont, and this is our experiment, the silica grains. You see Stokes number is much lower. We even added glycerol in the water to further reduce the Stokes number. And so if grains are frictionless, there is no hysteresis. But here, if we turn on the friction by putting ions in, then we have a large hysteresis. So it seems here that the hysteresis of the avalanche angle, it's not really inertia that matters. It's more the friction between the grains. Okay. And so we tried to go a little bit further to understand this, and we tried to make the link of this behavior, hysteretic behavior, with the rheology of the suspension. And so to do this, we use the rotating drum as a rheometer. And how do we do that? So the experiment is the following. We rotate the drum at a constant rotation rate, right? So we have a constant avalanche angle. And then we stop the drum, and we just let the avalanche relax until the grains stop moving. Okay. And it's just see qualitatively that for frictionless and frictional grains, the dynamics is very different. It takes a very, very long time for frictionless grain to relax. And it relaxes in a finite time for frictional grains. And from these curves, we can extract the rheology because theta, the angle of avalanche, gives you the friction coefficient of the suspension, right? And from the rate of decrease of theta, if you do mass conservation here, you can estimate the shear rate in the layer that flows. Okay? If you have the shear rate, you can estimate the viscous number, J. Okay. And so what we find is that frictionless and frictional layer of grain, they don't have at all the same rheology. So the frictionless system, it follows a monotonic rheology, which is a power law of the viscous number. But when we have friction, it's non-monotonic, and you clearly see on the data that here there is a critical velocity or viscous number below which the avalanche cannot flow. Right. And so these results suggest that inertia is not required to see hysteresis of the avalanche. And it shows how interparticle friction changes the rheology of the granular layer, which can be monotonic or non-monotonic. And with this, we can explain the hysteretic cycling of the avalanche we have in the rotating. Okay. And okay, and so just a summary slide here, and the picture of the people I worked with. So there is Cécile Claveau, Antoine Desrues, Hugo Perrin, and Baptiste were postdocs and PhDs. And Baptiste now has a generous position in FAST. And so every day I work with Henri Lucier and Yoel Forter in the lab in Marseille. And we are also collaborating with Mathieu Via, who is at EPFL now in Lausanne. Thank you for your attention.
Thank you very much. Questions?
Yeah, so everything I presented here is scalar, and people are working on developing this on the 3D tensorial form. So everything in reality is tensorial. So there are some anisotropy. For the particle stress, for instance, when you shear like this, the normal stress is not the same as in all directions. But that's a good point. Yeah, it's a good. Yeah, that's a good point. I never thought of that. Yeah, but yes, there is an anisotropy in all of this, which I put under the carpet here. Yeah, so we call it the friction coefficient of the suspension, which is different from the friction coefficient of the grain. So it's a coefficient that characterizes if I apply pressure P on the grain, how much tangential force do I need to put to shear the system? Just like you do not friction.
Your series is one of the previous slides when you show the stages around time. Yes, exactly that one. The right hand side, so you suggest that the angle at which the avalanche stops remains fairly the same all the time, while the one at which it's triggered exhibits some kind of
exactly. So what you see that it seems that the quasi-static friction coefficient, so the minimum here would be always kind of the same, but the starting angle would have more fluctuations. Yeah, it's true. It's true. If you want to know why, it's not so clear. But measuring a starting angle is in practice, we see always more fluctuations. Yeah, there can be many reasons. Experimentally, there are many reasons why you see more, because depending on how you load, how fast you load, if you have weighted, if there is aging, if there's a kind of stuff that can be.
I think that one from the one of the images that we showed, which can be dramatic when there's a flow houses. I think that the angle at which the avalanches are triggered is the most critical.
Yeah. Actually the difference sets the amplitude of the event.
So predicting that one is not often.
No, not at all. no. And it, yeah. And say it again. Your question is if we expect this to be flatter and this to be more fluctuating. I mean, we have not studied this, but the star, some people have tried to do this, but you have a layer at rest and then you increase the stress. So what we do here, when you keep rotating the drum, this means that mu increases because it increases progressively tau. And then at some critical mu, it starts flowing, right? And there are interesting fluctuations in this critical mu, but there are also a strong time dependence, aging dependence on this starting mu. So in the present experiments, we didn't really investigate this very much. It would be interesting to. Just the main feature that in one case there is this and not in the other was the main questioning aspect we had about this problem. But there would be many other things to do. Yeah. If you could have rods, let me see. Actually, that could be interesting. Yeah, probably. But it all depends. Why so dramatic here? It all depends. I mean, all of this business depends by how much you shift the critical volume fraction when you go from frictionless to frictional, for instance. So maybe we could suspect that these rods, frictional rods, maybe they jam at even lower volume fraction. So you would have even a larger difference between this. So you extend the domain at which of viscosity you can access. So that would be nice to have silica rods maybe and yeah.
At some point, you said that we changed the comparison force by changing as in the salt.
Yeah, exactly.
My question was whether it would be as a means to change the external means to change the basic force, for instance, by changing the balance polarization.
Okay.
Change the
Yeah. So this I'm not experts at all in this physical chemistry stuff. So what I know here is that that's well characterized that you can change the range of this force.
I think the polarization
yeah. So in the Metzger constant, you have the permittivity. Yeah. But how would you change in situ? Do you have ways to change in situ the permittivity? That's okay. 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 No, but why not? Yeah, maybe. Okay, if he can also play on the permittivity, yeah. Tim? Yeah, of course. So of course, there's lots of groups that work on. So everything I've said is about low Reynolds number conditions. And then there are extensions of all of these rheologies. So for instance, there was a recent work in our lab to see how do you transit from low Reynolds to inertial regime. What sets this transition? How are the rheological affected by this inertial transition? There's ongoing works And there are already a lot of results on that. Also for sedimentation, you can also consider effect of inertia.
Your grain size in your model, are they always the same size?
So it's a good question actually. So the rheology of granular system, you've seen it doesn't depend on the grain size. It's not a parameter that enters in the yeah. No, there is not the grain size. Although it's not completely true in a sense because so this is the simplest like steady state rheological models, but there are a lot of people are working, for instance, on non-local effects. So when you're close to a boundary, and then you can have a dependence of the rheology on the ratio of the system to the grain size. So in this case, this ratio can matter. So if the grains, if it's be dispersed, okay. Actually, usually when we do experiments, we mix a little bit. We try to have something not too monodispersed because this is a pathological limit, a little bit that can crystallize. So we try to have a mix two different sizes to avoid crystallization. Yeah. And for the size also, where the size matter is also physically to get to shear thickening suspensions and have such that the repulsive force between the grains becomes significant. The grains must be small enough, so below 50 microns. Above 50 microns, you don't have shear thickening because the repulsive force is negligible. Okay.
States of below the shear thickening solutions, suspensions, do they exhibit coarsening?
So what do you mean by coarsening? Ah. So what would you have? Okay, so if you wait, I mean the problem we have, for instance, if you use cornstarch, is that it ages. So if you leave it too long in time, the rheology changes. So this is kind of a coarsening. So what for all of these measurements, we prepare all the time a fresh new suspension for measurements. So there is no aging effect. If aging is what you hear, like what you mean by coarsening?
Well, not necessarily. Dynamically, that you would start to have a series of fronts, and then they would have effectively over.
Okay, so maybe okay. Maybe you mean that it becomes what we see actually. Maybe where is the? I don't know if we see it on the movie. I mean, we try to stay close to the onset, so the waves are pretty linear. But here already, you can imagine that the front of the waves is very steep. So there is it becomes very rapidly non-linear. And if you are inclining even more, then you can have lots of things going on, like merging, doubling of. I mean, there is a zoo of. So here we try to stay just at the onset where things are quiet, but plenty of stuff going on. Yeah.
By the way, on that, and for the speed of the fronts is the same as the speed of the front.
You see?
They seem
So,
to go faster, right?
Yeah, the waves go a little bit faster than this front. Yes. Yes. I don't know what. Maybe because there is this the wetting of the front at some dissipation, and so it slows down the front a little bit. But once it's yeah.
Any questions?
So, well, you don't want to heat maizena too much that you cook it. This is usually how people use it. But we stay at room temperature now. We don't see a temperature effect, but there is a group in Zurich run by Lucio Isa, where they manage to. So what they do, it's very beautiful what they do. Maybe I have a picture. Yeah, this is this group. They engineer the surface of colloidal particles. So it's quite amazing what they do. So this example is a particle that are the shape of a raspberry. So they control the roughness to control the rheology, but they can also control the chemistry. And I know that they have attached binded polymers that deploy or shrink depending on the temperature. And so they have a system where they can control the rheology of the shear thickening by changing the temperature. Yeah, this is also now options that are available to change the rheology. Yeah. Yeah.
Out of curiosity, you were mentioning at the beginning that you're going to stay on the right-hand side of your graph. Where you
Yeah, no, I didn't. Yeah.
And you didn't go into the gray zone.
Yeah. It's good.
If you go there, probably temperature fluctuations start to matter.
Yeah.
Since you have long-range interactions, you can have funny things like ensemble equivalence, or you can have part of your systems that behave differently than the rest. Have you investigated that? Can it explain some of the negative, like susceptibilities or negative behavior that you see?
Yeah, actually, okay. So actually, we started from the simplest case, and then I've talked about this region, like 15 micron, the cornstarch, where they start to be interactions like this. So this can lead to shear thickening. But actually, you could also have people have shown that you could have no repulsive force, but just Brownian motion. And that would also lead to shear thickening rheology and negative slope rheology, because you can see this thermal fluctuation as an effective potential or repulsive force. And so
Do you understand that?
And yeah, people have right. You can write that as an effective force, effective repulsive potential, and then you get all of the phenomenology of the shear thickening. Yes. Yeah.
So I think we have a few questions dancing around this before, but what has anyone tried, to work, say, with an electrical or magnetic rods, that you go along with an external field, a variable strength. I mean, in a sense, the diode, the anisotropy of the properties of the system. Has that been sort of systematically like that?
Well, systematically, I don't know, but I know that some groups play with this kind of stuff. Like, for instance, in Nice laboratory, Infini, there is a George Bossis working with this kind of suspensions, but particles can be anisotropic, and so he plays around changing the orientation with an external electric field or magnetic field. Yeah. So people have looked at the rheological response of suspension under an external field. Yeah.
So there is a well-established examples in plasma physics, the Taylor and Hackenauer problem, which is basically a bunch of charged rods and even basically two-dimensional structure with an external magnetic field. And it seems to me that you might be able to actually make this kind of system into a game like this, and then the granular suspension. It's very interesting.
All right, thank you for all of your questions.
So let's thank you again.